Marcel here. Welcome back. In this video, we are going to prove Tao's uncertainty principle at last, which we've been working towards for the last 4 videos. Recall in the last video, we proved a theorem called Chebotarëv's lemma, and I just wrote it again here in case you forgot. So it says that if Q is a prime power of P, a power of the prime P, and omega 1 through omega k are distinct roots of unity, so I guess distinct qth roots of unity, distinct qth roots of unity, and if n1 through nk are integers that are all distinct, pairwise modulo p, then the k by k matrix formed by putting omega I to the nj at the ijth, at the ith column and ith row and jth column has non-zero determinant. Okay, and this is all we're actually going to need to prove Tao's uncertainty principle. Now, we've already talked about what Tao's uncertainty principle says. It says that so if f is a function from zp to the complex numbers, then Tao's uncertainty principle says that the size of the support of f plus the size of the support of the Fourier transform of f has to be at least p plus 1. And we do need here zp. We need p to be prime. Recall in our very first video, I think it was the very first video, we did some examples right here. Let's just go very, very far back. So if we're just talking about, we're going on a little journey here. We did some examples like a really long time ago of a function. Okay, so here, this is 3 is prime. So here we have 1, 2, 3, 4, and that's p plus 1, right? But here we actually have 4 is not prime, and we made a function whose support has size 2 and whose Fourier transform has support of size 2 as well. And 2 plus 2 is 4, which is not quite p plus 1, which is 5 in this case. Well, n plus 1 because 4 is not prime. And so we see that the assumption that p be prime in this cyclic group is actually necessary. Okay, but we're going to show this bound. And we're actually going to show a little bit more, but I'll state that later. First, let's translate this theorem into a corollary that's kind of in the language of, the language of Fourier transforms, okay? So, sorry, something keeps knocking here. It's a stapler or something? Okay. So, yeah, let's call this a corollary of Chebotarëv's lemma. Okay, so let P be a prime, and let A and B be subsets of ZP, and I use that to say to mean the cyclic group modulo P with size of A equals size of B. Okay. So the linear transformation that's this transformation. I ran out of space. Also, it's messy. CA to CB, let's call it T, given by TF equals F hat restricted to B, okay, is invertible. Okay, so there's some notation here. So CA is a set of all functions from A to C, but we'll think of them as, because A is a subset of ZP, we're going to think of them as, so CA is the set of all F from ZP to C such that the support of F is a subset of A, okay? And likewise for CB. So you can see this is also restricted to B. That just means make it 0 outside of B. Okay, so you can see that this is going to be a linear transformation. Actually, we'll kind of write that explicitly in the proof. And we just want to show that that's invertible. And it'll be a corollary of Chebotarëv's lemma. Okay, so for short, we'll just write Z equals ZP. Okay, so recall that the sets chi u for u in z and fx for x in z. Okay, and we defined this in the second video. Let's just do this right now because I doubt you remember. So chi u of x, these are characters for each u. It's e to 2 pi I, what is it, xi, well, sorry, it'd be xu over p, okay, because it's just a cyclic group. And fx is a function on the dual group, actually. It's fx of chi, just evaluates chi at x. Okay, so we defined that a long time ago, and I'm halfway through a sentence here. Recall that the sets, these two sets, are orthogonal bases for the set of all functions from z to c and the set of all functions from z hat to c, respectively. Okay, so we showed this in the second video. We remembered any two distinct characters, or if you have two distinct characters, you take their inner product, you should get 0. If they're the same character, then you should get 1, and so that's an orthonormal basis, actually. And we showed that for this one, it's not quite orthonormal, but it's still orthogonal. Okay, that's all we'll need here. So in the first basis, by the Fourier inversion formula, okay, because f of x is a sum, right? So let's just write it out. F of x is the sum of all alpha in z, f hat of alpha, chi alpha of x, right? And is that right? Yep. Okay, so f is represented by so f is the vector. As a vector is f hat of 0, f hat of 1, all the way to f hat of p minus 1. Okay, and then likewise, so in the second basis, so there's a basis from functions on the dual, of functions from the dual. In the second basis, we just use the definition of Fourier transform, and we find that f hat is Fourier transform is an expectation. So it's actually 1 over p times the vector f0, f1, all the way down to f p minus 1. Okay, so we just kind of explicitly writing our functions as vectors in these spaces by the with these bases. Okay, so now if we set omega equals e to the 2 pi I over p, then we see that by the Fourier inversion formula once again, if we write out the Fourier inversion formula, it says that f0, f1, all the way down to f p minus 1 is equal to, okay, it's this matrix, chi 0 of 0, chi 0 of 1, all the way down to chi 0 of p minus 1, chi 1 of 0, chi 1 of 1, all the way down to chi 1 of p minus 1, and so on, chi p minus 1 of 0, chi p minus 1 of 1, all the way down to chi p minus 1 of p minus 1. Okay, and it's times the vector of all the f hats. So f hat of 1, f hat of p minus 1. And that's just, you get that by just, look, so this is, we apply it with x equals 0, x equals 1, all the way to x equals p minus 1. You can see that it's going to be this sum, right? So the first row it's that nice sum there. Yeah, so like if put 0 here, you get 0 here, and yeah, sum of all alpha and z. Okay, so that's the Fourier inversion formula, just written out. It's applied p minus 1 times and then written out as a matrix vector multiplication. But this is equal to, let's rewrite this as, powers of this root of unity that we have. It's omega 0 to 0, omega 1 to 0, all the way down to omega p minus 1 to 0. Then in the next column, we have omega to the 0, omega to the 1, all the way down to omega to the p minus 1. Okay. And last one, we have omega to the 0 to the p minus 1, omega to 0, omega to the 1 to the p minus 1, all the way down to omega to the p minus 1 to the power p minus 1. Times the same vector, f hat of 0, f hat of 1, f hat of p minus 1. Okay, so that's all nice. And now we're, we can see that we're kind of in the domain of Chebotarëv's lemma, because, so hence, letting k equal a equal size of b, okay, the matrix of t, remember, is you apply f, and then you restrict to a. So you apply f, but since f has support contained in a, only some of the rows matter. So only some of the columns matter, sorry. And then we restrict it to b, so only some of the rows matter. So the matrix of t is, we have to scale by p over here, but, right, like, 1 over p, and it's 1 over p, 1 over p. Okay, but it doesn't really matter. The point is, the matrix of t is sum k by k minor of the matrix above. Okay. But now, letting the zi be omega to the I for I in A, letting n and j, equal j for all j in B. Okay, the matrix satisfies the hypotheses of Chebotarëv's lemma. Chebotarëv lemma. Okay, and so it's invertible. And this is going to be very useful in the proof of Tao's uncertainty principle, which we will state right now, even though we've stated it kind of already. Just make it complete. So theorem. This is due to Tao, Terry Tao, of course. Okay, so let P be a prime number. There's no R. Okay. If f from zp to the complex numbers is a non-zero function, then the size of the support f plus the size of the support of f hat is at least p plus 1. Okay, so we'll probably use this 0th norm to mean the size of the support. Okay, but that's not all this says. Actually, this part's kind of easy now that we've done what we did above. Conversely, if A and B are non-NP subsets of ZP, such that A, size of A plus the size of B is greater than or equal to P plus 1, then there exists some function f from zp to complex numbers such that the support of f is equal to a and the support of f hat equals b. Okay? So it's quite a lot stronger. It's saying, not only do all functions have this satisfy this inequality, if you satisfy this inequality, like if some set satisfy this inequality, then there is a function whose support is a and the support of the Fourier transform is b. Okay, so let's do the proof. So like I said, the first part is going to be pretty easy now that we have proven the little corollary above. So suppose towards a contradiction, that f is non-zero, but by non-zero I mean it's not identically zero, but the size of the support of f plus the size of the support of f hat is less than or equal to p. Then letting a equal the support of f, and okay, so the support of f hat is not necessarily disjoint, right? It doesn't mean that these two sets are disjoint and have size less than p, but so let a be the set support of f. We can find a set b such that the size of b is equal to the size of a, and b is disjoint from the support of f hat. Okay? So we didn't say that the support of f is disjoint from the support of f hat, but we can find a set of the same size that is disjoint from the support of f hat. Okay? Now, let's give a new. Okay, so what does this mean? This means that, sorry, where am I in this proof? Okay, so the Fourier transform of f, so the Fourier of f restricted to b is 0, right? Because b intersect the support of f hat is 0. On the other hand, we can apply the corollary to a and b to find that t is invertible. Okay, but this is a contradiction, right? Because then tf equals 0, but f is not 0, and t is invertible, and those contradict each other. So that's this first part. So the support of f plus support of f hat has to be have to have the sizes add up to more than p plus 1, or at least p plus 1. Okay, so now we have to prove the converse. So now, okay, so now we assume that we have a and b with sizes adding up to at least p plus 1. It's actually easier when it equals p plus 1 exactly. So we'll do that first. First, we handle the case where size of a plus size of b is equal to p plus 1. Okay, so in this situation, we choose a prime. It's gonna satisfy some cardinality thing. We choose a prime with the size of a prime equals the size of a, such that A prime union B is equal to ZP, and then A prime intersection B is equal to 1. Okay, so just like before, we have the sizes adding up, but they don't add up in like, we don't know that they add up in a disjoint way, right? It's sort of like almost disjoint way, but we can just change A, shift A around so that we have it exactly like this. So their union is ZP, and their intersection has exactly 1 point. Let's call that, so say A intersection B is equal to some singleton set with X in it. Okay, so apply the corollary. So again, we're going to use that corollary to Chebotarëv's lemma. With not A and B, but A and A prime, to find T from set of all functions from A to C, set of all functions from A prime to C, and T has to be invertible, is invertible. All right. So now we let G in, so it's a function from A prime to C. Let's just not be confusing. So G is a function from A prime to C, B such that Gx is not equal to 0, and Gy equals 0 for all y in A prime that are not x. Okay, so it's really just, it's a function where on just this 1 point x, and everywhere else it's 0. So there is a function f, because t is invertible, we can invert it. So there's a function f from A to C such that t of f is equal to g. Okay, meaning the Fourier transform of f restricted to A prime is equal to g. So since the support of f hat is a subset of A prime, okay, the support of f hat is a subset of A prime complement, okay, and then x. Why is that? Because so support of, so f prime, f hat, you restrict it to A prime, it's only on x, right? Now we don't know what f hat is. It could be like outside of A prime, it could be lots of other things. So it may have support in A prime complement, but inside A prime, it only has support on x. But this is actually equal to b, right? So we have f hat, size of support of f hat is less than or equal to the size of b. And also we have, since support of f is subset of A, we also have this, right? The size of the support of f. Sorry, it's not B, it's supposed to be A. But now, because A and B, size of A and size of B add up to exactly p plus 1, we need to have equality here, or else we'll violate the first paragraph, which we already proved, right? We already proved that it's got to be at least p plus 1. We proved in the first paragraph, these two have to be at least p plus 1. And since we found that they both have to be less than A and less than B, and A and B add up to p plus 1 exactly, so in order to not contradict what we proved in the first paragraph, we must have support of f equals A and support of f hat equals B. Okay, so that's the case in which we have equality. in the case we don't have equality, we're going to just apply this over and over and over again. And we'll see how that is done right now. So, in the case where size of A plus size of B is, sorry, I'm going to make sure everything fits. Size of A plus size of B is strictly greater than P plus 1. Okay, we can set. So let's call it big S is equal to the set of all A prime B prime, such that A prime is a subset of A, B prime is a subset of B, and A prime plus B prime, their sizes add up to exactly P plus 1. Okay, so we're going to find sort of an instance of the last paragraph inside this. This set is finite, obviously. So we'll number its elements. We'll index them A1, A1, B1, A2, B2, all the way down to AS, BS, where little s is the size of big S. Okay, so from the previous paragraph, there exist functions f1 all the way down to fs such that for all 1 less than equal to I less than equal to s, the support of fi is equal to ai, and the support of fi hat is equal to bi. Okay, so that's just applying what we already know in the case that it's exactly P plus 1, A plus B. Okay, so now let f equal lambda 1, lambda 1 f1 plus, all the way down to lambda s fs for some lambda I in C. Okay, so we're going to pick the lambdas, well, later. So to be chosen later. Okay, so no matter what we choose, okay, we must have, because, you know, it's linear, right? So the supports, because each of the supports of the FIs they're part of the AIs, and all the AIs were contained in A. So I guess it's clear. I hope it's actually clear that the support of F is a subset of A. And then because the Fourier transform is linear as well, all the Fourier transforms, the Fourier transform of this guy will just be the, you add up all the Fourier transforms with the exact same lambdas, right? So since Fourier transform is linear, you know, let's write it out. F hat is equal to lambda 1 f1 hat plus lambda s f hat s. Okay, so support of f hat is a subset of B. Okay, and now we show, it remains to show that we can choose lambda I such that we have the opposite inclusions. So A is a subset of support of F, and B is a subset of support F hat. Okay. Well, how do we do that? So for X and A, let Vx be this set. So it's set of all lambda 1 up to lambda s in the vector space C to the S, such that this sum I equals 1 to S, lambda I fi of x, okay, so this is a fixed x, remember, is equal to 0. Now, these are complex numbers, right? And we have s degrees of freedom here for the lambda i's, and we have one non-trivial linear equation, right, that they have to satisfy, linear constraint. So this is a subspace of C to the S of codimension 1. Meaning it's a subspace of dimension S minus 1. Okay, so similarly, let Wx equal all to lambda 1 up to lambda s in C to the S, such that the sum of I equals 1 to S, lambda I f I hat of x is equal to 0. And sorry, this is for for x in B. Okay, and again, it's also a subspace of codimension 1. So now, observe that that this union, so union of all x in A, V, x, and then union of all x in B, W, x. So this is a union of finitely many codimension 1 subspaces. So, I mean, imagine like this. We have the union of a bunch of codimension 1. So this is dimension 2, and these are codimension 1, so they're just lines. We have a union of all these subspaces, okay? No matter how, if we have a finitely many, no matter how big this finite number is, the volume is going to be 0. So, and all we need is just to have a point outside. It's the same but like if you take the union of like finitely many planes in 3 space, you're going to get, there's a way to make this, rigorous about Lebesgue measure and stuff like that, or because we're working the complex numbers, not the real numbers, but just it's true. It's obviously true. So is a finite union of codimension 1 subspaces. Thus its complement is non-empty. Okay, and so, really its complement is very, very non-empty. It's almost the whole thing, right? And we can choose lambda 1 up through lambda s, such that the resulting f has f x equals 0, not equal 0 for all x in A, and f hat of x is not equal to 0 for all x in B. Okay, and that's all we needed. Okay, so we've proven Tao's uncertainty principle, and that's what we were working towards for a long time. So if you stuck around, thanks for watching all these videos. There is one more video. It's kind of a bonus video. We're gonna, it would be kind of anticlimactic or to, prove this theorem and not show a cool instance of how you use it. So in the next video, we're going to use Tao's uncertainty principle to prove the Cauchy-Davenport theorem, which we've actually proven before on this channel. But we're going to give a, it's a Fourier analytic proof. It's actually in the book Additive Combinatorics, which I'm following. Tao and Vu actually call it a Fourier algebraic proof, which is interesting. I might be the only Fourier algebraic. I've just never heard about, Fourier algebraic methods. It's not, so I thought that was kind of funny. So we'll see that Fourier algebraic proof of Cauchy-Davenport's theorem in the next video. So, and that'll be the last video of this series. So see you then.